All right, to continue with section 5.1, we can now talk about continuous probability function in a general form. So again, a continuous probability function is a CDF, a cumulative distribution function, that's absolutely continuous. So it's continuous, there are no breaks, it's never changing or skipping anywhere. It's just a nice, like, kind of smooth curve, right? And if the distribution x is continuous, then x is called a continuous random variable. And the probability between C and D is the area. So I think that we need to think about this probability in the area. So let's consider the function that is what we remember as a horizontal line. I know. If f of x is equal to a constant, we know that is a horizontal line. In fact, it's going to be a horizontal line on a domain from 0 to 20. So let's go ahead and draw a figure that represents this function. So let's draw the first quadrant. Let's go ahead and mark 0, and here's 20. Okay. And let's just go ahead and label anywhere on the y-axis 1 over 20, which is just f of x. Notice if I drew a line from 0 to 20, and then bounded it by a vertical line at 20, I have made a well-defined shape called a rectangle, as you know. And this area is the probability. So when I want to find, in here it says, find the probability that the random variable is between 0 and 20. Well, what is the area of a rectangle? The area of a rectangle is just base times height, right? Our base is the length, 20 minus 0, right? I would just subtract. And then the height is going to be this y value. I went up 1 over 20. So this becomes 20 times 1 over 20, which is equal to 1. So the probability of 0 between x and 20, the probability of x being between 0 and 20 is equal to 1. And therefore it makes sense because notice that I shaded the entire rectangle, right? The whole rectangle is shaded. The probability is 100%, meaning the area is 1. Okay, kind of going with this. Now let's kind of play with this, right? Let's not make it so plain Jane, all right? Let's go ahead now and go to the next probability we want to find. And so I would go ahead, I have an area representing, see, construct a figure representing f of x, representing the area 5 to 12, and find the probability from, and this should be 5 to 12. Okay, make sure you note that. I will also note that. Okay, and so taking the same figure above, right? So the 0 to 20. So here's 0, here's 20. And then here is 1/20th, which is f of x. And I'll draw a rectangle. Okay, and so now let me represent the area 5 to 12. So here is 10, here's 5, and then 15. So if I did that, here's 5, and 12 is about right, almost a little halfway. And if I shaded that area, it looks like just a little box inside. So notice my area should not be 1, right? It should be smaller than 1 because I'm not taking the entire area as I did up here. Okay, so now let's go ahead. I did the first part. I constructed the figure representing the area, and now the probability that x will be between 5 and 12 is equal to, once again, I have a rectangular shape, base times height. So the base here would be, this was 12, so it would just, the distance between 5 and 12, which would be the difference, right? And then times the height, and notice the height stays the same as 1/20th. So 12 minus 5 is 7 times 1/20th, and that becomes 7/20ths. So the probability that x is between 5 and 12 is 7/20ths. And I know what you're thinking. You're like, this is kind of easy. I know, don't you love continuous distributions, right? It's so nice, nice shape. You don't really have to think about much. Okay, now let's continue and let's do something that's not a little as comfortable, right? So now let's go ahead and continue with the function 1/20th, and we'll represent a figure representing the area from between 2.3 and 7.5. So still draw the first quadrant as usual. And here's 0, here's 20. And then you still have 1/20th as f of x. And so now it gets a little tricky because here's 10, here's 5, and here's 15. So I'm going to use red here in this case because 2.3 is like a little before halfway here, and 7.5 is midway between 5 and 10. But yet the height, it's going to start here, yeah, and do this. And so if I just shade this a little, so that's the area. Now, to calculate this area, you would just do the probability the same way. You know, just because the numbers don't look as clean doesn't mean the process isn't clean. Remember, the processes stay the same. Problems change, but the processes don't. So again, it's still the shape of a rectangle. And so base times height. So the base here, you know, you're going to use that same method because that may not be so obvious, that distance. So still subtract and then multiply by the height, which is still 1/20th. So when you do that, you'll get what you'll get is 0.26 or 13 out of 50. So you'll keep the process no matter what, right? Draw the rectangle. I find that to be helpful. And so here I wanted to note what we were doing, like, because it seems like we were doing the same thing. We were drawing a rectangle, shading, base times height. That's exactly what we'll be doing. So in the note, I went ahead and noted that, like, if we have a function where we have between C and D, and we want to find area, any area inside C or D, whatever it is, then the area will just be b minus a times the constant function f of x. Right? So it's A and B could be either, the A and B boundaries doesn't necessarily always have to be inside C or D, right? Like we had every case here. We had the actual end bounds to B, right? the C and D, right, 0 to 20. Then we had an A and B inside 5 and 12, or 2.37.5. But the idea is just use the shape and multiply base times height.